Hello, class. We are going to start chapter 3 and looking at the application of derivatives. So far, we learned about derivative of function, we know how to calculate them, but now it's time to see what piece of information or why our derivatives are helpful. And in this first section, section 3.1, in this video, we are going to start by seeing the application of derivatives in identifying extreme values of the function. So in this video, we are going to see what are the critical numbers of the function and how can we use the derivative, the first derivative and the second derivative in order to identify them. So let's first start by interesting point. What do we mean by interesting point? Is that when you have a function, what are the interesting points that we want to study? For example, one of them is called global or absolute maximum. You can either go by global or absolute. I oftentimes use the word absolute. Absolute maximum or absolute minimum. So what is absolute maximum and absolute minimum? So suppose you have a function. The function gives you a set of output values, right? Absolute maximum, if it exists, maybe it doesn't, but if the function has an absolute maximum, for example, f of c, let's say f of c, which means that this output, we call that, you give input value to the function, it returns you output value. Now, among all of these output value, the one that is greater than anybody else, so that output value in this definition says f of c, that output value which is greater than or equal all other output value, that's called absolute maximum, if it exists. And what is absolute minimum? Absolute minimum is that you look at the output of this function, the one value that is smaller than any other output, that is called the absolute minimum. So just, I know, look, this is the formal definition. I want to give you like an way of informal way of looking at uh, absolute extreme values, so that you have a understanding of what is this without notation. So suppose you have a function, right? And it takes the value from the domain, right? So you can give input values and it returns you output values, right? Output values. Now, look at the set of all output value, which we call it range, right? This is a, suppose you can look at the entire output value, the range of the function. The greatest value here, the greatest value, the greatest greatest value is called absolute max, absolute maximum of the function, and the smallest value in the range, the smallest value, that is called absolute minimum, which means that it is smaller than any other value in the range among output values. Okay, so these two are two interesting values that we would like to study if they exist. For example, look at these pictures. In this picture, you can see the graph of two functions. On the left, look at the graph. The graph is first increasing and decreasing. Look at the point V. At point V, your function reaches the maximum height. What do we mean by maximum height? It means that the height of the function, the height of the graph at this point V is greater than any other height. So that is an absolute maximum. That height, which is 40 something, it's greater than 40. That is the greatest output value, greatest height. So that is called absolute maximum. Now look at the graph on the right side. The graph on the right side, in the graph you can see point A, point B, and point C. Now look at the entire graph. In the entire graph, the greatest height, happens at the point C and G of C. You see, so for the input value C, the output value G of C has the maximum height. So G of C is the maximum, absolute maximum, because it's greater than any other height in this graph. Now, another extreme value that we like to study is called local max and mean, or also relative max and mean. I oftentimes go by local. What does it mean? It means that at those points, they are not the greatest. You don't have the greatest output value, or you don't have the smallest output value. Instead, around their neighborhood. So if you look at them in around a local neighborhood, they are the maximum or they are the minimum. For example, in this picture on the graph on the right, the graph of function g of x, you see 2 points, A and B. Look at the input value, the point for input value A and B. At A is not the greatest height. B is not the smallest height. But what happens is that if you just focus or cut your graph in a close neighborhood of point A, then the height at A is greater than the rest of them. So like you have a picture like this. Let me try to draw that. So I'm trying to draw this picture. So it goes up. So it goes up, it goes down, it goes up, and then it goes down. This is C and G of C. We said that G of C, this is the absolute maximum. Why? Because this height is the maximum height. It's greater than any other point. But then at A, this is the point A and F, G of A. Input value A, output value G of A. And also B, which is kind of right here. So this is B and G of, maybe I put it up, B and G of B. So what happens is that, okay, neither of them are absolutely greater than or smaller than any point. But let's focus on this graph just over a close neighborhood to these input values. Like graphically, for example, look at this place. So this is your A, this is A. Now look at the neighborhood around A, a local neighborhood, like here up to here. Just focus over these values around A. What is the graph? The graph is here. Then it's like you just cut this portion of the graph, remove the rest. Then yes, over this interval, over this neighborhood, then A reaches the maximum height, which means that G of A is greater than any other value, any other height over this green region. So this is called, okay, it's not absolutely maximum, but locally it is maximum. So it's called local maximum of the function, because locally for its neighborhood, yes, it is maximum. And over here, look at this one. So for example, here, if you look at this small neighborhood around B, so for these input value close to B, then the height, the function has the smallest height at B. So this is gonna be the local minimum, because it has the smallest height around, for the points around B. Then G of B, the height for B is the smallest for the values around B. So then this was an example. So actually in this picture, the graph on the right is an example that it has absolute maximum, g of c. It has two local extreme value, local max and local mean, and it doesn't have any absolute minimum because the function is going down, down, down forever. So there is no absolute minimum. And the function on the left side just has one absolute max. There is no absolute mean, and there is no local extreme value. So I mean, we need to know these terms, but then the function may or may not have these values. But in general, when we talk about, so far we identify extreme values. We defined extreme values for a function. Could be absolute, could be local, but those are extreme values. But the general family, let's define a more general family of values for a function. Critical values. Critical values. What are critical values in general? It contains those extreme values as well. So it's like you have the extreme values. So you have maximum, minimum values of a function. So suppose you have the extreme values of functions of a function, then suppose this is the set of extreme values of function, then the bigger set is called critical values. Critical values which also include the extreme values. So what are the critical values? Any point, look at this graph, look at this picture. We have 1, 2, 3, 4, 5 graphs in this picture. From left, let's start from left. On the left, we have this graph, which is concave down, right? So I like to write on this. Let me copy this. Let me see if I can paste it here. Yeah, I think might be able to write on this. Okay. So this one, the first one. So the first one, you see the graph is concave down, right? And graphically, you see that there is a maximum here. You see that there is a maximum and it's absolute maximum, but I don't care here about absolute or local. I just say there is a max. There is a maximum here. So this is the extreme value. And look at this point. Okay, at this point, actually, the problem is that while there is a maximum, okay, maybe I say it this way. Maybe I say it here this way. So this is also maximum. But there is a difference between the graph on these two graphs. The difference is that in the first one, we are able to draw the tangent line. You see that? We are able to draw the tangent line, which its slope gives us the, what is the slope of this tangent line? Is 0. So that means the derivative at this point is 0, right? So in the first picture, the graph is concave down. The graph has a maximum. And because of that maximum, the tangent line, because of the shape of the graph, the tangent line is flat. So it has a slope of 0, which means that the first derivative at that point is 0. But we don't have the same situation in the second graph because we cannot draw the tangent line. You see that? And this is the case that although there is a maximum, but derivative doesn't exist. So I may say f prime does not exist because we cannot draw the tangent line. What about the third one? In the third one, actually derivative exists. Look, you see? We have you can draw the tangent line. You see that at this point, at this red point, you can draw the tangent line. It's flat. So the first derivative is 0, but it's not extreme value. You see that? My point is that this point is neither max nor mean. What about this graph? Here you can draw the tangent line. It's flat. the derivative is 0 at this, the slope is 0, so the derivative is 0 at this point, and it's a minimum. It's a minimum. It's an extreme value. And in the last one, again, the problem is that we cannot draw the tangent line, so the derivative doesn't exist. The derivative at that point does not exist. So you see, we have just look at the derivative, the behavior of derivative over these on these points over these graphs. The first one to the left, derivative is 0. Second one, derivative does not exist. Third one, derivative is 0. Fourth one, derivative is 0. The last one, derivative does not exist. These are examples of critical point. So what are the critical numbers of a function? Any point that either the derivative is 0 or the derivative doesn't exist. So critical is more general than maximum and minimum, because, for example, we say that, look, we say that this, and this all are critical points of the function, but all of them are not extreme value. For example, this is neither maximum nor minimum. So critical points is a more general family than extreme values, because a point can be critical, but it doesn't have to be maximum or minimum, like the middle example. Okay, so what is the definition of critical point? If a point is critical, if and only if the function, so let's say point A is critical, or X, or whatever letter you want, is critical for F under two conditions, if and only if either the derivative at that point is 0, either the derivative of the function at that point is 0, or the derivative of the function at that point does not exist. If you have any of the case, that point is gonna be critical point, and any of these points on this graph is an example of critical point. Okay, so in this picture you are seeing example of critical point. In 3 of them, derivative is 0, and in 2 of them the derivative does not exist. So here is the formal definition of critical point. We say that a function has a critical point at like input value c if the derivative at c is 0 or the derivative is undefined at that point. Now, it's easy to determine critical points because you can take the derivative. Look, it all depends on the derivative. So if the question is find a critical point of a function, just take the derivative and find the points that either the derivative is 0 or does not exist. So the first step is C. The second step is that which one of these critical points are minimum, which one are maximum, which one of them is neither maximum nor min. So to determine that, we need some tool, and it's called the first derivative test and second derivative test. So I'm going to start with first derivative test. That's a tool to help us to identify extreme values. So it says, this test says that if you have a critical point of a function, and the function has a relative maximum, local max, if the derivative change sign from positive to negative, or in another, look. If you have a, suppose, maybe zoom out. Okay. So suppose you have this. So again, look what does this test says. It says, suppose you have a critical point. So you know that a function at P has a critical point. Now, it is a local maximum if the derivative change sign from positive to negative. Why? Because look, if derivative change sign from positive to negative, that means the function is increasing and then change to decreasing. You see that? So if the function is, then it gives us the local maximum. You see that? So this is the case that you have a critical point, right? And then, so graphically, this is going to be the shape. And then f prime change sign from at this point, let's call it P. So the sign of f prime is positive, but then it changed to negative. Graphically, the function was first increasing and then it changed to be decreasing. First increasing, then it changed to decreasing. So that's going to give us a local what happened? I'm sorry about this. My whiteboard is a bit fuzzy. Okay, so this is gonna give us a local. I'm sorry about this problem. I don't know what's wrong with this whiteboard. Sorry about that. I had to open a new whiteboard. Okay, so I have to sketch this one more time. Here is the situation. Look, we are describing the first test, the first derivative test. Suppose P is a critical point for function f, okay? So we know that P is critical for f. So x value equal P is a critical point for f, right? And if, so then f has a relative maximum if f prime change sign from positive to negative. So what does it say? It says that, look at f prime. So what does it say? It says, look at the behavior of f prime around P, f prime. It says if, f prime, the first derivative. It says if it change sign from what to what? From, it change sign from positive to negative. From positive, meaning that if the derivative is positive and then it changed to negative. So what does it mean graphically? Graphically means that if f prime is positive, if the derivative is positive, that means the function is increasing. And then suddenly at P, it changed the sign. So that means it changed direction and it becomes decreasing. So yes, of course, that gives me a maximum. You see that? So then this is gonna be a maximum. So it's gonna be a local max, local maximum. So that's the first derivative test that says, look at, when you identify the critical point, then look at the signs of the first derivative around that point. And if the sign changes from negative to positive, okay, we can derive the conclusion. Look, if you have a case that at P, the sign of the first derivative changed from negative to positive. So what does it mean? It means that the graph was decreasing up to P, and then it changed to be increasing afterwards. So what does it give me? It's gonna give me a minimum, you see? So in this situation, you're gonna have a local minimum at this critical point. So that's called the first derivative test. So we can always look at the first derivative and depends on the sign of the derivative identify whether we have a local max or local mean. For example, let's see one application of this test. It says let f be a function whose derivative is given by this formula. Determine all the critical numbers of f and decide whether it is a max or mean or neither of them. Please pay attention that in this question, we are not given the formula for f. So we don't know what is its original function. Instead, we are given the formula for the derivative, okay? Because if I had the formula for f, I could just look at its graph by GeoGebra or any calculator, and maybe I could say it by using the calculator. But here I have to use this test because I don't know what is f. I just have the information for the first derivative. So let's do this example. So this is example 1. The derivative of this function is e to the negative 2x minus x times x plus 1 square. Okay, the question says, determine all the critical values and then identify them whether or not they are extreme values or whatever they are. Okay, so we have the first step is to determine the critical values. What was the definition of critical value? Any point that it's the derivative is either 0 or the derivative does not exist. So we just need to, so first of all, the derivative exists. You see that? The derivative, the formula of the derivative is given, and this function is defined for any x value. So derivative exists any place. So it's just zeros of this derivative. When and where the derivative becomes 0, that gives us those flat tangent line. So the first step is find critical values. Okay, how should we find the critical value? Set up f prime of x equals 0, or solve it for 0 so that we can find the values that make the f prime, make the derivative equal 0. So which means that we need to put the formula of the derivative equals 0 and then solve it for x. Okay, so notice that this function is 0. e to the 2 negative 2x is exponential function. Exponential function is never 0. Remember, it's always, this is the graph of exponential function. It's always e to x, e to any exponential function is above x-axis. So that's not going to be 0. It's either 3 minus x. So it's either 3 minus x that is 0, or x plus 1 squared that is 0. So one value is 3 and the other value is negative 1. So these are the critical values. Okay, so we identify the critical values. What are the critical values of this function? 3 and negative 1. The second step. After we find the critical, so again, what are the critical values of a function? Any value that the derivative doesn't exist, so here the derivative exists, and any value that makes the derivative 0. In this example, 3, the x value 3 and x value negative 1 makes the derivative 0. So these are critical points. So maybe I write this down. The critical values are the critical values for function f, for f are x equal 3 and x equal negative 1. That's it. Now the second step is identify the critical, identify the extreme value. Maybe I should, the extreme values, or I don't mean the extreme value, I mean identify the rule of this critical value, whether or not they are extreme. How should I say that? So it says determine all critical numbers. Yes. Decide whether a relative max, mean, or neither of them. Okay. So identify if any of them, I mean any of um, three. Identify, how should I say? Identify if any of them is extreme value. Identify if any of critical values provide, gives something like this, extreme value, something like that. Okay, so this is the second step. So yes, we know there is a critical, we know that 3 and -1 are critical values, but do they give us like maximum, minimum, or none of them? This is our second step that we need to do. How to do that? We are going to use the first derivative test, which says, look at the signs of the first derivative around that point. So that means I need to look at the sign. What are the points? One of them is -1, the other one is 3. These are the critical value of f. But what I need to look at is the derivative, the sign of derivative around these points. Okay, sign of f prime over these intervals. So let's see. So this is f prime. Where is f prime? This is f prime. You see that? Maybe I repeat it. It's f prime. I'm going to repeat it here. F prime of x is e to the -2x, and then 3 minus x, and then x plus 1 squared. That's f prime, right? So the question is, what are the sign of this function around this critical value? Okay, so at 3 and -1, -1 and 3, we are looking for sign of f prime, the first derivative around these values. Okay, so this function has exponential function. Again, recall that exponential function, e to x or e to any power, is always above x-axis. So it's always positive. So this piece is always positive. And this factor, x plus 1 squared, it's a square. So this is also always positive. Any value, always positive. Any value that is squared, it's always positive. So technically, the only thing that determines the sign of the whole function is 3 minus x. So it's just the only factor. So let's see. 3 minus x. What is the sign before -1? Like, let's say at -2. So at -2, 3 minus 2 is going to be 5. So it's positive. So that means the function is positive. The derivative is positive before -1. What about after -1? For example, after -1, like 0. Between -1 and 3, 0. So 3 minus 0 is 3. It's still positive. You see that? So over this region, still the function is positive. What about after 3, like 4? At 4, 3 minus 4 is gonna be negative. Okay, over here, the sign is gonna be negative. So what does this tells us? Using the first derivative test, which you already saw the first derivative test up here. This is the first derivative sign. If we see a change, in the sign of derivative, that is gonna give us extreme value. And here, look, I don't see a change around -1. You see? Around -1, around here, around -1, there is no change in the sign. Before -1, the function is positive. After -1 is positive. So this is neither max nor minimum, nothing. Neither max nor minimum. So this is not an extreme value. However, at 3, we see a change. The function changed from positive to negative. Recall the first test derivative. It says that if it changed from positive to negative, that means there was a change from being increasing to become decreasing. So that gives me a local max. So there is a local max. So there is nothing, -1 is not extreme value, but 3 is a local max. This is the way that we use the first derivative test. We first find the critical points, and then we look at the sign of the first derivative around those critical points. If there is no change in the sign, so that's not an extreme value. But if you see a change in the sign, that is gonna be a local extreme value, and depends on the change. It could be positive, or it could be max or min. And if you want a more detailed solution, you can look at the solution from the textbook. So it's first finding the critical points. The critical points are 3 and -1, and then determining the sign of the first derivative around -1 and 3. So the function is increasing and increasing around -1. So that doesn't give me any max or mean. But then around 3, the function is first increasing and then it becomes decreasing. So that's going to give us a local mean. Okay, so we learned about first derivative test. We saw an application of it. There is another tool that is also great in identifying the role of critical values of a function, and that's the second derivative test. Okay, look at this graph, this picture. There are 4 graphs. So all of them, let me see if I can write on this picture. So in this picture, these 4 graphs have something in common. These points, these critical points, look at the critical points. This is a critical point. This is a critical point. This is a critical point for this function, and this is a critical point. What they have in common is that the tangent line is flat, you see? So all of them has the tangent line that is flat, which means that the first derivative at those points is 0. The first derivative is 0. The first derivative here at this point is 0. The tangent line is flat. The first derivative is 0. The tangent line is flat. The first derivative is 0. So if I just want to rely on first derivative, okay, the first derivative at all of them are 0, but the behavior of function is different. For example, here, here we have a local max. Here we have a local mean. And in these 2 points, it's neither max or mean. So you see, it is not enough to rely on first derivative, because if we just want to rely on first derivative, they all have the first derivative of equal 0 at these points, but they behave different. So we need another tool that that helps us to identify points like this. Okay, so we need something more to help us to identify points like this, which second derivative comes along. Recall that the second derivative tells us about concavity. Remember, if the second derivative is positive, the function is concave up. If the second derivative is negative, the function is concave down. Remember that? So we can use that to formally define the second derivative, introduce it. So suppose again you have a critical number, you have a critical value like this graph. The derivative at all of these 4 points is 0. So they are critical values, right? And then, so the derivative is 0. And then the second derivative is like I can describe it from here. Look, for example, here we have a local max, right? So in the first in the first picture from left, you have a local max, right? Okay, so graphically, can you tell anything from the second derivative of this function? Okay, we have a local max. The function is concave down. We know that if the function is concave down, that's gonna be the second derivative is negative. Do you remember? So that's the connection between second derivative and maximum minimum. So again, one more time. You have a critical point. The tangent line is flat. The first derivative is 0. The function is concave down. The second derivative is negative, then that's a local maximum. What about local mean? Look at the graph. The function is concave up at that point. So the second derivative is positive. So here the observation is that, okay, if you have a critical point, the first derivative is 0, the second derivative is positive. So the function is concave up. That gives you the local minimum. And what about here? So here, the function is, let me see if it is, okay. At first, I'm gonna get to these last two graphs later, because here the second derivative test only gives us the result for the first two cases, local max and local mean. So it says, you have a critical point, derivative of that critical point is 0, second derivative is not 0, but it is negative, right? So it's a local max. Second derivative is positive, so it's a local mean. Okay, so I think the textbook wants me to first show you an example of this case, and then after that, I'm gonna get to the last two cases. Okay, so first let's see an example of this. So in this example says, let f be a function. Again, we don't know what is the formula of the function, but the derivative, the first derivative formula is given. It says construct both first and second derivative sign chart, fully discuss where f is increasing and decreasing, concave up and concave down, and then identify the extreme values. Okay, look at this. So I'm gonna put it right here. So it's 3x to the 4 example function. The derivative, the first derivative is as 3x to the 4 minus 9x squared. That's the first derivative, right? And okay, I know what the question asks for the rest. We need to use the first derivative and second derivative test in order to identify the extreme values and possibly sketch the graph of this function. We don't know what is the formula of the function, but we have the formula for the first derivative. Okay, so the first thing is first find the critical point. Find critical points. That means solve, set the derivative equals 0. So 3x to the 4 minus 9x squared equals 0. So here we have to factor it. So it's I can factor 3, I can factor x squared. This is gonna be x squared minus 3 equals 0. We can factor more. This is gonna be 3x squared, x minus square root of 3, x plus square root of 3 equals 0. So values are 0, x equal square root of 3, and x equal negative square root of 3. These are the critical values, okay? Second, now look what I'm gonna do. Identify the extreme values. Identify extreme values. Max and mean values, maximum, minimum values. Okay. So, what are the critical values? The critical values are negative square root of 3, 0, positive square root of 3. I need to know sine of f prime, first derivative. What was the first derivative formula? One more time. I need to identify the sign. The first derivative is 3x to the 4. I'm going to put it here. Derivative is 3x to the 4 minus, oh, we have the, by the way, we have it in the factor format. Maybe I write it in the terms of factor format. The first derivative in the factor format is 3x squared, x minus square root of 3, x plus square root of 3. Okay, so let's see. This is always positive. Always positive. If you have a value greater than square root of 3, this is going to be positive, right? And this is going to be positive. So this is going to be positive for any value greater than a square root of 3. If you want, you can try some value, but for any value greater than square root of 3, this over this region, the f prime is going to be positive. What about between 0 and a square root of 3, like 1? For example, 1 is here. Try 1. This is positive. 1 plus this is positive, but 1 minus a square root of 3, 1 minus 1.4, this is going to be negative. So negative times positive. So I think this is negative. Okay. If I'm not wrong, I think this is negative. What about between negative square root of 3 and 0? Like negative 1, something like that. Negative 1 plus 1.7. This is going to be positive. Negative 1, negative square root of 3. This is going to be negative. Positive times negative. So I think this is negative. But you can, if you're not sure how to identify positive, negative, just use a calculator. Try a value in between these range. Just use your calculator. Whatever is the sign, that's going to be the sign over between those critical values. And finally, for any value smaller than negative square root of 3, this is positive. This is negative. This is negative. But negative times negative is gonna be positive. Again, if you are not sure how to quickly determine the sign of f prime on top of your head, it's okay. Just use a calculator, try some values, and see if it is positive or negative. Okay, so what does this tell us about function f? Function f, so this says that the original function f, is positive. So over here is increasing. So it's increasing, and then it becomes decreasing, right? And then here again, it's decreasing because it's negative. And then the derivative become positive. So the slope of tangent line is increasing. So this is going to be increasing. I also put the behavior of the original function over these intervals. Okay, now let's apply the second derivative rule. So we need to find the second derivative and then figure out the sign of second derivative, because that's going to help us finally to determine these values. Because so far, okay. So that's for now. Okay. So what is the second derivative? The second derivative, maybe I put it right here. So the second derivative is gonna be 12x to the 3 minus 9 times 2 is 18 times x. So this is gonna be, the second derivative is gonna be, we can factor 6 and x. And this is gonna be 2x squared minus 3. So when we set this equal 0, when we set this equal 0, then we get either x is 0 or x squared is 3 over 2. Or in another word, x is positive, negative square root of 3 over 2. Okay, so these are the values that the function is the zeros of the second derivative, right? Okay. So what I'm gonna draw is that, look, at zero, because among these, only this one is critical value. This is not a critical value, but zero is critical value. So zero matters, right? I should use the second derivative sign around zero at least, okay? So around zero, like for example, let's say 1. At 1, what happens is that here, look here, at 1, this is going to be positive, 2 minus 3 is going to be negative. So this is going to be negative because we try 1, 6 times 1 is positive, then 2 minus 3 is negative. What about before 0, like negative 1? At negative 1, it's going to be negative 6 times negative 1 square is positive, and this is going to be negative, so it's going to be positive. So this side is going to be positive. You see that? Okay, now, so we determined that. Now let's put this together. So what does it mean? It means that we can go further, by the way. We can go further. Let's try some more values because I want to also determine the concavity, right? I also want to write about concavity of the function because we want to draw the graph. So far I know that the function here is second derivative is positive, so it's concave up. Here is negative, so it's concave down. Okay, what about the rest? Actually, the function at square root of 3 over 2, yeah, it's gonna change the concavity. Okay. So far, I know the function is increasing and decreasing, and it's concave up. So this is gonna be the function. Let me think. The derivative is 0. I think I need more about concavity. So I need to try something like a square root of 3. My point is that I need to know about the concavity over here between less than negative square root of 3. Okay, something like negative 2. Okay, it's gonna be, the second derivative is gonna be 6 times negative 2. 2 times 2 squared is 4. Yeah, so 6 times negative 2, 2 times 4 minus 3. So this is gonna be 8, this is gonna be positive, so it's gonna be negative. Okay, it's gonna be negative. So this is gonna be negative, which means that the function is concave down. Okay, and then what about after the square root of 3, like at 2? At 2, it's gonna be 6 times 2. 2 times 2 squared is 4 minus 3, 8 minus, this is gonna be positive, so it's positive. So here is positive, the function is positive. So, sorry, the second derivative is positive. That means the function is concave down. Okay, I think now we can draw the graph. Look, so I know that the function, look, I'm going to draw the graph. Over here, the function is increasing, but it's concave, it's increasing, but it's concave down. So the function must go up like this. And then it becomes decreasing and it's concave up. So it's going to be like this, if I'm not wrong. And then it's again decreasing, but it's concave, and it's concave down. Wait. I think I made a mistake. It's concave down. Yes. So it's like this. Look. So maybe I do it this way. Look. So I know the function is concave up, concave down. So, and it's decreasing. So I need to draw something that is decreasing, but over here is concave up, and then it's concave down, okay? So concave up, and then concave down, right? And then it changed the concavity to become concave up. So it's like this, and it's increasing. So something like this, and then here is increasing, okay, and it's concave down. So something like this. Let me check if I draw. This is the whole idea, but I don't know if I messed up in my calculation or somewhere in the sign. So let's check the work in the textbook. So yes, the critical values are negative square root of 3, 0, and 3. It's increasing, decreasing, decreasing, increasing. The same thing here. It's increasing, decreasing, decreasing, increasing. So far the same. And then for the second derivative, okay, so the second derivative is negative. Oh, okay, I see. Because I didn't incorporate those 2 points. That's why I got a funny graph, because I didn't incorporate this point. In my graphing, I said, okay, forget about this. But no, in fact, we also need to, when we want to determine the concavity, we should say 0, negative square root of 3. Actually, I should have drawn a separate line. I should have separated these two and just allocate this for the second derivative. Okay, so like your textbook, look, your textbook has like figure or graph for the sign of first derivative, in which we can see the increasing, decreasing behavior of the function, and it has a separate, number line to show the sign of the second derivative in order to determine the concavity. And yes, when you put this together, it's gonna be like this. So the difference between where did I miss? My missing part is that, okay, I miss these two values, a square root of 1.5. So it changed, the concavity changes at a square root of 1.5. So if I'm gonna fix my graph, I should just incorporate the square root of, I just need to incorporate this value, this two value. I'm gonna incorporate it into the same line. So I didn't incorporate this value. This is x equal positive and negative square root of 3 over 2 or 1.5. Square root of 1.5 is gonna be here, right? Negative square root of 1.5 and positive square root of 1.5. I didn't incorporate that into my graphing. That's why my graphing is fuzzy. So it's gonna be like this. I'm gonna fix it and show you how to fix it if you are also in the same situation. So at negative 3, look, it changed the increasing, decreasing. So the graph goes up because it's increasing. Look. So the graph is going up and then it's going down because look, because at negative 3, at negative square root of 3, the first derivative changed the sign. So the function is increasing, look, the function is increasing and then it changed to decreasing. But then at this point, the concavity changes. It's down, now it changed to be up, right? And then again, the concavity changes. So at 0, because before 0 is positive and then after that it's negative. So again, we have a change of concavity up to this point. And then again, we have this decreasing and increasing function. So in my original drawing, I didn't incorporate a square root of 1.4. That was why my graph didn't look like the graph here, because I was missing in this picture, I was missing the point B and D, the point for a square root of 1.5, positive and negative. So that was not a good idea. So we should incorporate all the critical points, all these values. Okay, and then when you put all together, you can come up with the shape of the graph of this function. So to summarize, the graph has a local, you see, it has a local minimum, local maximum. So we have 3 critical points, right? Let's go back to the first step. We have 3 critical points. So at negative square root of 3, this gives us a local max. At 3, we have a local mean, local minimum. You see that we have a local max and local mean. And 0, actually, this is called inflection point because the concavity changes, but I'm gonna get to that in a moment. But for now, in terms of extreme value, we have in this picture A, at point A, we have a local max. At point E, we have a local mean, local minimum. So inflection point is any value that your function changed the concavity. So from concave, that's called the inflection point. So in this example, actually there are 3 conflection points, B, C, and D, because the concavity changes. You see here is like in this picture, it's first concave down, then it changed to be concave up. Then it again changed to be concave down. Then again, it changed to be concave up. So there are 3 concavity points. And you can also verify that by looking at the graph of the function. So if I want to complete my writing, 0 is inflection point. And also, these are inflection point, positive and negative, square root of 1.5, inflection points. So we identified the rule of each one of these values. We have how many values? Negative square root of 3, negative square root of 1.5, 0, positive square root of 5, positive square root of 3. So there are 5 interesting values in this function, and we determined that one of them is local max, one of them is local mean, and the other are just inflection points, which means that the points that the function changed their concavity. Okay, the next question is basically, the next activity is just a practice for concavity. I recommend you guys to do these activities. It's good. It helps you to better understand the meaning of the application and meaning of these tests. So there are good exercises here. Finding the critical points is always finding the points that make the function 0, and then you need to determine if it's an inflection point or 0. I recommend you to do these exercises on your own. So first try to do it on your own, check your answer. And then if you have question or if you don't know how to do the part, click on solution, and then you can see the step-by-step solution of these questions, okay? So for example, find the inflection point of this. Okay, so that means you need to take the, oh, did I say that the second derivative is 0 at inflection point? I think I forgot to mention that. Because that's the technique, how to find the inflection points. Yeah, just as we saw the how to find extreme value or critical value, to find inflection point, you just because the second derivative is 0 at those points, just set the second derivative equal 0. So if you have a question like this that says find the inflection point of f, the idea is that take the second derivative. I'm going to show you this one. Look, you are given a function, and the question is find inflection points of the function. So it's not enough to take the first derivative. You need to find the second derivative of this function, set it equal to 0, and then solve it. You need to solve this equation. Solve it for x. Solve this for x. When you get those x value, those are um, um, gonna be the nomination for inflection points. I have to show you one more thing. So you take the first derivative, you take the second derivative, and if possible, like here, you factor it, and then you set them equal 0. So in this case, when you set them equal 0, one value is 1/8, the other value is -7. So these are going to be the point that uh, you can also verify that the second derivative changes sign. So they are going to be the inflection points. And if you're not sure about like any of this, just go back to the summary. In the summary, we put, it's like a cheat sheet that what's what. So I am afraid if because we introduced so many things in this video, I'm afraid if you get lost. So let's go over what we learned in this video. So the critical values of a function are those values that whether the first derivative is 0 or the first derivative doesn't exist. So if the question says find the critical values of a function, you take this first derivative, set it equal 0, find those zeros. Those are critical value. Now, if you have and if f prime is positive, then f is increasing. If the derivative is negative, the f is decreasing. That's obvious. But from here, we get the first derivative test result, that you identify the critical values. Then you look at the signs of the first derivative. If you have increasing, decreasing, positive, negative, that's going to be a local max. If you have negative to positive, that's going to give you the local mean. And finally, so if you have a function that you can take the second derivative, if you have a horizontal tangent line at any point and the second derivative is not 0, then the sign of the second derivative tells us about the concavity of the function. And hence we can say whether f has a max or mean at that point. So here is the idea. You take the first derivative, set it equal 0. I mean, imagine you have a point that the first derivative is 0 and the second derivative is negative. Okay, so that means the function is concave down. So here you have a local maximum, okay? So simple. The first derivative is 0. The second derivative is negative. F is concave down, so f has a local maximum here. But if the first derivative is negative, the second derivative is positive. Sorry. If the first derivative is 0 and the second derivative is positive, so the function is concave up, so the function has a local minimum at that value. And here is the last point. What if both of first derivative and second derivative are 0? What about that case? Like in this question, look, let me show you. Like 0 in this question, look at 0. Look at the 0 in this question. 0 is a value that makes the first derivative 0, and it also makes the second derivative 0. So at 0, both of these functions are 0. So in that case, f is not, doesn't give us any local extreme value, and most likely this is an inflection point, that it's neither maximum nor minimum. It's just the point that the function changed the concavity. For example, from being concave up, it changed to be concave down. So in case you think you missed any point of this lesson, just go over the summary. You can find anything that you need. And then again, I recommend you to do the exercises of this section so that you will be ready for the homework assignment of this section. That's all about this. Thank you for watching this video. I'll see you in the next video.